Alrighty, guys. We're gonna do a review now, final exam review. Hopefully everybody's studying well. This will have the largest impact on your grade overall, beyond what I can do. I got my periodic table and my common ions, and I got my formula sheet nearby, ready to go. Got my calculator ready to go. All right, what is a mole? A mole is a number. It is 6.02 times 10 to the 23rd. It's Avogadro's number. Now, it means different things. If you take that many atoms of carbon, it means they weigh 12.01 grams. If you have that many atoms of carbon, so I guess you could say a mole of carbon is 12.01 grams, but that's not the technical definition. The definition is it's a number, just like a dozen is 12, and a couple is 2, and a ream is 500. A mole is 6.02 times 10 to the 23rd. Now, a mole of atoms weighs the molar mass on the periodic table. So a mole of carbon atoms, 6.022 times 10 to the 23rd atoms, weighs 12.01 grams. How is Avogadro's number related to it? They are the same. They are the same number. It's a mole of carbon atoms. So 12.01 grams of carbon is a mole of carbon atoms, or 6.02 times 10 to the 23rd. Okay, when we say molar masses, we mean the molecule. We don't mean empirical formula, we mean molecular formula. So we have a molecular formula here of FeCO3. So I have 3 oxygens times 16, enter, plus a carbon, which is 12, enter, plus an iron, which is 55.85, enter. So I have 115.85 grams per mole. That is the molar mass of FeCO3, 115.85. Here's a little more difficult. I have to multiply this times everything inside, so I know I have 12 oxygens, and I know I have 3 chromiums, and I know I have 2 aluminums, and then I'm going to add all that up together. So 26.9 times 2, that's my aluminums, plus 3 times my chromiums, which are, let me find a 52, plus 12 oxygens, 12 times 16, and I put all this in parentheses, and 401.8 grams per mole. So those are the 2 answers there. Okay. 25 chromiums. Yeah, it's all those dang chromiums. So heavy. 51 apiece, 150 just in chromiums. Anyway. Convert 5.68 moles of phosphorus into atoms. Well, remember, these are all single box conversions. These are one box conversions where we're converting from moles to atoms, or from moles to mass in grams, or we might need 2 boxes where we go from grams to molecules, but for the most part, we're going to use single box conversions because these are not stoichiometry, these are just conversions. Moles of phosphorus, and in 1 mole of phosphorus, there is 6.02 times 10 to the 23rd atoms of phosphorus. Atoms of phosphorus. Now, I'm going to work these out the long way, but again, you know that this is going to be multiple choice on the test. So 5.68 times, and I put this in parentheses, 6.02 times 10 to the 23rd. Close parentheses, and I get 3.42 times 10 to the 24th atoms of phosphorus. That should be a big number. If you get 7 atoms of phosphorus, then you've done something wrong. Consequently, if you get 3.42 times 10 to the 24th moles of phosphorus, then you're also equally wrong. know what is a small thing, an atom, so there are liable to be lots and lots of them, versus a big thing, a mole, which there will not be very many of them. There will be 10 moles, or 5.68 moles, or some nice round number, or 6.2 moles. Okay, so here they're giving me moles to grams conversion, so 6.2 moles of CO2, and we want to go to grams of CO2. And I know that in every 1 mole of CO2 there is, let's see, 16 times 2 plus 12, 44 grams of CO2 in every 1 mole of CO2, just adding it up. And so 6.2 times 44 grams is 272.8 grams. So the essential knowledge here is you have to know the molar mass of the compound so that you can say what 6.2 moles of it weighs. And the essential knowledge up here, well, I mean, you're given Avogadro's number on your formula sheet, so that shouldn't be much of a stretch. 6.022 times 10 to the 23rd. I've been using 6.02. It's okay. It doesn't matter. Pick your poison. Grams to molecules. So now I'm going to need either 2 boxes or 2 conversions. So I'm going to do it in 2 boxes just because by now you should get the hang of just doing that. So I have 36 grams of nitric acid, which is HNO3. And I want to go to molecules of HNO3. And so I know that for so many grams of HNO3, there's going to be 1 mole of HNO3. And I know that for every 1 mole of HNO3, there's going to be 6.022 times 10 to the 23rd atoms or molecules. Molecules of HNO3. Let's see, 3 times 16 plus 14 plus 1 is 63 grams. All right, 36 times parentheses 6.02 times 10 to the 23rd power, close parentheses, divided by 63, enter. 3.44 times 10 to the 23rd molecules, which, given that a mole is 63 grams, this is about a half a mole. This is half of 6.022 times 10 to the 23rd. That seems right. So again, we've got some answers here. I'm going to circle my answers too, make them a little more obvious. All right, find the percent of chlorine and iron chloride. Percent of anything is the percent is the part divided by the whole. And they tell you the part, find the percent of chlorine. So that's the part. Well, there's 3 chlorines. 3 times 35.45, enter. So what I have is 106.35, the part divided by the whole. And the whole includes those chlorines. So 106.35 plus 55.85 for the 1 iron is 162.2 times 100 is going to give me my percent chlorine. Okay, 106.35 divided by second answer is, times 100 is 65.6%. 65% chlorine. Don't forget that it's just the part divided by the whole. You just have to figure out what the part is. A lot of times y'all like doing the part divided by the other part, the 55.85. That's not going to work right. You're going to get some percentage over 100%. It's the part divided by the whole. And remember, the whole includes the part. Okay. Empirical formulas for the following. That just means I have to factor out the greatest common factor. Here I'm going to factor out a 2, and that's going to be C4H9. Can't do anything else with that. Here I'm going to factor out a 2. That's going to be CH3O. And here I'm going to factor out a 2, and it's going to be NO2. Once you get down to single atoms in a molecule, you can no longer factor that thing anymore, so it's done. That is the empirical. So this is the empirical formula, this is the empirical formula, this is the empirical formula, this is the molecular formula, molecular formula, molecular formula. You will see that the molecular formula is always some number bigger. In this case, twice as big. All of them twice as big. Exactly. Not always the case, but in this case, yes. Okay, the composition of acetic acid. This is the one y'all tend to forget. You tend to forget some part in the middle. You don't remember the mnemonic. The mnemonic is percent to grams, grams to moles, divide by lowest, multiply till whole. And you don't even have to remember the multiply till whole part. You have to remember percent to grams, grams to moles, divide by the lowest. And that's what you'll struggle with. So, percent to grams. Well, that's easy. That's just making it grams of carbon, grams of hydrogen, and grams of oxygen. Grams to moles. The way we go to moles, and the way, I mean, nowhere up here did we convert anything to moles, but you know how to convert things to moles. It's dividing by the molar mass. So if I divide by 12.01, that's going to give me moles of carbon here. And if I divide by 1.01 grams per mole, might as well write it grams per mole, this is going to give me moles of hydrogen. And if I divide oxygen by 16.00 grams per mole, it's going to give me moles of oxygen. Sometimes you just divide by the lowest, you divide them all by 1.01, and I'm like, what are you doing? That's not making anything into moles. Dividing carbon by hydrogen's molar mass doesn't give you anything. It tells you nothing at all. So what you really need is moles here. Make sure that you understand. I know up here you know how to do one box conversions into moles. Maybe you need to do that for each one. But anyway, I have 40 divided by 12.01 is 3.33 moles of carbon. I'm guessing this is going to be 6.66. 6.71 divided by 1.01 is 6.65, 6.64. And 53.29 divided by 16 is 3.33. So the lowest mole total is either that one or that one, but it doesn't matter. You gotta do this. And what I end up with, and what's very obvious here, is that I end up with C1, H2, O1. So that is my empirical formula, because I'm dividing by the lowest mole total, equal to 2, equal to 1. All right, an unknown compound is found to have a molar mass. That means it's its molecular mass. That means as it actually exists out in the universe, not the empirical mass and not the empirical formula. The empirical formula is just the lowest ratio of things to each other. So they gave me an empirical formula. Well, I know that carbon is 12 plus 2 plus 16. That's what? 26, 27, 28, 29, 30. This is 30 some odd grams approximately for the empirical formula. And the molecular formula is roughly 3 times bigger. That's all you're doing, is you're comparing the empirical formula size to the molecular formula size. Well, I don't have anything but a mass for this and a formula for this. So I either have to convert this to a formula, you can't, or this to a mass, you can. So I converted this to 30 grams per mole, and then I divided the molar mass by that empirical formula mass. Empirical formula mass. And it's always going to be a whole number. It's always going to be 3 times bigger, and you're going to multiply all those subscripts by that number. So C3, H6, 3 times 2 is 6, O3. That is my molecular formula. Oh, man, I almost got off screen there. C3H6O3, because the empirical formula is 30 grams, the molecular formula is 92 grams, it's 3 times bigger. I have to have 3 times as many atoms. You multiply all the subscripts times 3. I don't know how else to say that. Okay, carrying on. This one might be in a couple parts, so we won't sweat it too much if we have to stop and make another part. Or we might just let it run, let it be a really long video. Alright, stoichiometry, give the mole ratios for the following reactions. So KClO to O2, that is 2 to 3. Mole ratios are simply the coefficient compared to the other coefficient in the order they give. So they said KClO3 to O2. They want that molar ratio. So 2 KClO3s to 3 O2s. Well, here we have 3 O2s to 2 KCl's. 3, 2, 2, 3. Hopefully mole ratios are the easiest thing you ever give on a test. If they asked me 28 mole ratios, I'd be happy to provide them. Alright, so now we got to start doing stoichiometry. That means we have a balanced equation. That means that we're going to have a heart of the problem where we have moles of one thing over moles of a different thing. If you don't have that part of the problem, frequently y'all like to ignore the rules of dimensional analysis and you get sideways. You take a guess at how many boxes you need. You don't know. You need 1 box for conversion. So if I'm going from moles of lithium chloride to moles of AuCl3 to moles of lithium chloride, then I need 1 box. I need to go from moles of one thing to moles of the other thing. That is 1 box. So I have 4.5 moles of AuCl3. And I want to know how many moles of lithium chloride, LiCl, I can get out of this. Well, I know that the units here back into the top box, so this is moles LiCl. And I know the units here diagonally must be the same. Always, 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 never not the same. If you see different units here and here, you have done something wrong. Go back and fix it. Now, this is the heart of the problem. Luckily, it's the only box I have to deal with here, so LiCl, it looks like I have 3 moles of that for every 1 mole of AuCl3. Okay, 4.5 times 3. 4.5 times 3 is 13.5 moles. That's assuming this reaction goes completely. When we do stoichiometry and gifted chemistry, we assume that these reactions are always going to completion. Alright, so now I have 2.75 moles of lithium, and I want to go to grams of gold. That means I have to go from moles of lithium to moles of gold to grams of gold. That's going to be 2 boxes. 2.75 moles lithium. And I'm going to grams of gold. So I have moles of lithium, grams of gold, 1 mole of gold. This is the heart of the problem where I have moles of gold over moles of lithium. I'm going to go ahead and write heart of the problem. And in gold there are, let me look up here at my periodic table, there's 197 grams of gold in every 1 mole of gold. And let's see, we got to go moles of lithium. Now the heart of the problem has to come directly from the equation itself. So 3 moles of lithium, moles of gold is 1 mole of gold. All right, it's a math problem. 2.75 times 197 divided by 3. I ignore all the ones, and I get 180.58. Grams of gold, moles of lithium chloride. Okay. We are going to keep going. Wait, someone's messaging me. Let's see who's messaging. Okay, don't care. All right. How many grams of gold chloride are needed to produce 143 grams of lithium chloride? So what I'm going to need is 3 boxes. Grams to moles, moles to moles, moles to grams. So I'm starting out with 143 grams of LiCl. And I want to know how many grams of AuCl3 I'm going to make. So I'm going to go through this the way I normally do dimensional analysis. I know that the units have to cancel diagonally. I know that anywhere where I write grams of anything, on the other half of that box is 1 mole of that stuff. Every single time. It's never 2, it's never 5, it's never 60, it's 1 mole. Same over here. Grams. AuCl3 is going to be 1 mole. AuCl3 below that. Okay. 35.45 times 3 plus 197 is 303.4 grams. And LiCl is 6.941 plus 35.45, which is 42.4. And here we have moles of LiCl. And here we have moles of AuCl. How do I know that? Because diagonally they have to cancel. Grams LiCl, grams LiCl. Moles LiCl, moles LiCl. Moles AuCl, moles AuCl. Grams of AuCl is the last units I'm left with. Those are the units of my answer. So here, how many moles of LiCl? 3. It comes directly from the equation. 3 moles of LiCl. And how many moles of AuCl3? That's going to be 1. And now it's a math problem. 143 times 303.4, enter, divided by 42.4, enter, divided by 3, enter, is 341.1 grams of gold chloride. Alrighty, we're going to keep going. I think I'm going to get to 30 minutes and then I'm going to stop and then I'm going to do another video. I'll do part 2. Okay, solutions. What is the difference between dissociation and solvation? Describe what happens during both processes and what types of compounds use them. Alright, so I'm going to use sugar. And a sugar molecule, C6H12O6, that's the molecule of sugar. It's not ionic, it's covalent. So if I have a bunch of molecules of sugar, C6H12O6, C6H12O6, and then I'm going to dunk them into a beaker full of water. What's going to happen is those molecules are going to separate from each other. That is solvation. Solvation. The same thing happens when ionic compounds go into solution. The same thing happens. They first solvate, which means the molecules separate from each other. But then they go the extra step, and the molecules get surrounded by the waters. And man, if you're ever taking AP Chem with me, I really need you to know which end of a water is negative and which end of a water is positive. This part is the dissociation. So both covalent molecules and ionic molecules will solvate first. They will go through solvation where the molecules and the formula units will separate from each other. I'm going to put this in a separate beaker. But then ionic compounds go through an extra step. The ions actually separate from each other. There are no ions in this covalent compound of C6H12O6 because there are no metals. So there are no ions, and it doesn't separate into ions. But this, let's say this is NaCl. It is a ionic compound, and it separates into a sodium cation and a chlorine anion in solution. That is the dissociation part. Solvation is where you get that immediate dissolving of all materials. Dissociation is where the ionic materials go the one extra step, and the actual ions themselves will walk away from each other because they are surrounded by waters. Okay, what three factors affect the rate of solvation of a solid in a liquid? Well, shake, bake, and break is what we want. Shake, bake, and break. So what we want is we want agitation, increase in temperature, and increase in surface area. So if you're trying to dissolve like a sugar cube, your best bet is to break it into a bigger surface area, increased surface area, by crunching it up and then throw it in there. Well, I just said the ways to do that. So yeah, I just indicated the ways that would increase the rate of solvation: increase the temp, increase the surface area, and agitate it. What factors affect the rate of solvation of a gas in a liquid? That's temp and pressure. Temp and pressure. Temp and pressure affect solvation of gas in a liquid. And if you want to get more gas to dissolve in a liquid, you want a high pressure and a low temperature. A cold Coke has more dissolved CO2 in it, hence its freshness and not its flatness, than a hot Coke. A hot Coke will have less of the dissolved gas in it, especially over time if you give it a minute. Okay, how many liters of... Okay, so this is a solutions question. So what we need is this: molarity equals moles over liters of solution. Okay, well, they've given me M. It's 1.25 M. And they haven't given me liters of solution. They actually want to know how many liters of solution it would take to do this. But what they have given me is grams, and I can convert those into moles. So 85 grams HCl, and I'm going to divide by 35.45 plus 1.01, 36.46 grams per mole. That gets rid of grams and gives me moles. 85 divided by 36.46 is 2.33. If I put 2.33 moles in here, in order to make a 1.25 molar solution, I can tell you exactly what I'm going to need. I need 2.33 divided by 1.25. I need 1.86 liters of solution, final volume. .86 liters of solution. So hopefully these guys don't give you much of a problem. Whenever you see solutions, you should write down the molarity formula. I don't know why you don't. I frequently see you going, how do I figure this out? How do I figure this out? How do I figure this out? If they give you a molarity, plug it into the molarity formula and see what else you could get there. Or if you have another piece of information, don't just stop and stand still and go, I don't know what to do here. Keep moving forward. Man, this thing is so blurry. Why is this thing so blurry? Oh well. I mean, I can't make it any clearer. If I get it closer, it doesn't make it clear. If I get it further away, it doesn't make it clear. That's about as clear as it's going to get. Okay. I'm going to stop this video here. This is part one. Part one will be pages 1 and 2.